Okay, we're eventually going to do stuff with our parametric surfaces. And just like with parametric curves, some of what we're going to do is going to have some requirements that the parametrization be sufficiently nice. And generally, when a parametrization is nice, we say it's smooth. That means a particular type of niceness. So I wanted to remind you what it means for a parametric curve to be smooth, because it's been a while since we worked with our parametric curves. And then that's going to generalize nicely to describing what it means for a parametric surface to be smooth. Okay. So R of t was smooth if R prime of t was continuous. So notice it's not enough just that R be differentiable. It has to be continuously differentiable. And even that's not enough. We also needed R prime of t to never be 0. Okay. And if I had those two things, a consequence of that was that we would have a continuously varying unit tangent vector. Okay. The derivative is continuous, so that's how I'm going to get continuously varying. But if the derivative was ever 0, 0 can't be tangent to anything because it doesn't have a direction associated with it. And 0 also has, the 0 vector has 0 magnitude. So if I have a non-zero vector, I can normalize it. So I can create a unit tangent vector. If I have the 0 vector, A, it's not tangent, and B, I can't normalize it to get a unit vector. Okay. So a consequence of being smooth was that we had a continuously varying unit tangent vector. Okay. So if I have R of uv and I want it to be smooth, it seems reasonable that we would require del R and del U and del R del V. The two partial derivatives would have to be continuous. So here there's just one full derivative. This would have two partial derivatives. So both of these must be continuous. We're also going to require that they not be 0, but we're going to go one step further than that. Okay? We're going to require that they're not 0 and they're not parallel. I can get all of that by saying that their cross product is not 0. So this is going to tell me that neither one is 0. Because if either one was 0, when I crossed it with the other, I would get 0, and we're not getting that. And they are not parallel to each other. Okay. That's going to be significant because if I take a look at this, this is generally going to be normal to my curve. But it can't be if it's 0. Okay. Now, why is that going to, sorry, not normal to the curve, normal to the surface? Why is that the case? Well, let's just take a look. Actually, let's just take a look at our sphere. Now, if you remember, we parametrized that sphere as r of theta phi equaling rho is constant at 1, so just sine phi cosine theta, sine phi sine theta, cosine phi. And what we determined is that if we took in the theta phi plane, if we took this rectangle, where theta went from 0 to 2 pi and phi went from 0 to pi, that would map to this sphere. Okay. And if you recall, our constant phi curves were actually just circles going around like so, and our constant theta curves were actually half circles connecting the top of the sphere to the bottom of the sphere. So here I've got this point right here that's the intersection of a constant phi curve and a constant theta curve. Now, if I take the partial of r, in this case it would be with respect to, let's say, theta. Okay. So along my constant phi curve, which is this circle coming around here, if I take the partial of that with respect to theta, I'm going to be getting a vector that's tangent to that curve. But that curve lies on this surface, so it's also tangent to that surface. Now, if I take a look at del r, del phi, that's going to be measuring the partial derivative that I get along a constant theta curve, where theta is constant but phi is varying. That's going to give me something that's tangent to that constant theta curve. Okay. But if it's tangent to that curve and that curve lies on this surface, it's tangent to that surface. So that's giving me two things that are tangent to the surface. If they're not parallel to each other, when I take their cross product, I'm going to get something that is normal to the surface. So this, if I know this is never zero, this is going to be normal to the surface. Now, I don't know how long it's going to be, but if its length isn't zero, I could normalize it. So if it's smooth, there's going to be a continuously varying unit normal vector. And in fact, we've got a nifty formula for that. So here I was using the example that my parameters were theta and phi, because I wanted to, in particular, look at that sphere. But in general, if my parameters are u and v, the principal unit normal vector that would be associated with a parametrization would be the cross product of the derivatives normalized. So, the definition of smooth, and I might ask for this, the definition of smooth is not that there's a continuously varying unit normal vector. The definition of smooth is that the two partials are continuous, and then you need to either say neither is zero and they're not parallel, or what's a little bit faster, you can consolidate all of that and say, and their cross product is not zero. Okay. So we'll be working quite a bit with smooth curves as we work through things. Now, one thing that's interesting here is I just used that sphere as an example. Now, technically, the parametrization of the sphere that we have is actually not smooth. If I look at r of theta phi equaling, sine phi, cosine theta, sine phi, sine theta, cosine phi. It's almost smooth. But if you remember, we go from 0 to 2 pi and 0 to pi here, so just restricting the domain to be this rectangle so that we get the sphere once. What we had determined was that the constant phi curves, so this is theta and this is phi, the constant phi curves were giving me circles around the outside of the sphere. But if phi is 0 or if phi is pi, I'm just getting a single point. So this entire line maps to this point at the bottom of the circle. And this entire line segment here maps to just that point right there. Now that's going to be reflected in one of the partials being 0. If I take a look at the partial, so that was holding phi constant, so the partial of r with respect to theta, that's going to be, or did I want phi? Well, let's calculate them both. Partial of r with respect to theta would be negative sine phi sine theta, sine phi cosine theta, cosine phi. No, I'm sorry, 0. This is the one I wanted. Okay, because there are no thetas there. So this is always 0. Notice if phi is 0 or pi, that makes both of these 0 as well. So at these places where an entire line segment maps to a single point, makes sense that the partial of r with respect to theta would be 0 there, because as theta changes, I'm not moving. I'm right here at this point. That's what it means for a derivative to be 0. Okay. So this parametrization of the sphere is not smooth. However, those are the only problems. Just when phi is pi and when phi is 0, and that corresponds to just 2 points on the actual surface. So it turns out that this is an ignorable problem. Okay. Everything that we can do with smooth surfaces and smooth parametrizations, we can do with this parametrization of a sphere. And if it was a sphere of a different radius, I just have a different constant in each of these terms. So it's close enough to smooth that the lack of smoothness doesn't cause a problem. Technically, what we really ought to do, but we're just not going to bother, is we really ought to say, well, if I just drew a little line here and a little line here, so I introduced an A and a B, and I then took the limit as A went to 0 from the right, and the limit as B went to pi from the left, then I'd be fine, because this would be smooth between A and B. The only problems are at 0 and pi. And essentially, what drawing that little line does is it just removes a little tiny portion of a sphere right at the top, and a little tiny portion here right at the top, and then as we take the limit, we fill in that gap. Not actually necessary to do that, but I did want you to be aware that that is not a smooth parametrization of the sphere. An issue that is going to come up is my cone. So if I have the cone z equals square root of x squared plus y squared, and I parametrize it as r of uv is equal to uv square root of u squared plus v squared, if I take the partial of r with respect to u, that's going to be 1, 0. Now this is just u squared plus v squared to the 1/2. So I would get 1 over 2 root u squared plus v squared times a 2u, and the 2's would cancel. Okay. That's not defined if u and v are both 0. It's not even defined, let alone continuous. Okay. So that's a problem. If I'm working with this cone, and I want to include that point, which is where 0, 0 would map to, I can't use this parametrization if I'm going to need to use these partial derivatives at all. And I want to mention this to you now because there are lots and lots of places where people do this wrong. Okay. If you were to use this parametrization, you would get an improper integral because it would be undefined at 0, 0. Okay. You could evaluate that improper integral and take the limit, and most of the time it's going to lead to the right answer. But it's really sloppy thinking. And unless you're willing to do the research and say, under what conditions do I know that an improper integral will A, converge, and B, converge to the thing that I was trying to calculate, just don't use that one, okay? Because we've got others that are much better. I could parametrize this, remember, as r of r theta, where x is equal to r cosine theta, y is r sine theta, and then z is r. I avoid the entire issue of those square roots. But I have seen solutions manuals that use that parametrization and ignore the fact that they get an improper integral. I know a lot of the online places where you can go to get homework help will ignore the fact that that's not a smooth parametrization, and they usually get the right answer, but they don't know that I'm going to be the one grading it, and I want the work to be right. And since we've got a perfectly good workaround so that we can have a smooth parametrization, you may not use this even if it does lead to the right answer, unless you want to go through the work of justifying, showing me that the improper integral converges and that you know it converges to the right thing. And I just don't think it's worth your time. So we'll just avoid that.